All right, so we're here with our Honor Stat students to talk about the material from Chapter 18. So we're going to be talking about sampling distribution models. And this is going to be the foundation for what we do for the next 4 weeks. Okay, so make sure you're paying attention. You're trying to understand these concepts. If you have not read the material for Chapter 18, that would probably be impressive if you did, since I didn't post the material, Douglas. Good job. I'm going to post that tomorrow so you can start reading Chapter 18 from the electronic online textbook. All right? Okay, so let's start talking a little bit about these sampling distributions. Now, today, I'm only going to focus on sampling distributions for proportions. Okay, so we're going to talk about, we're going to do an example with a sample proportion. And tomorrow, we're going to do the same thing, but with a sample mean. So we'll have units tomorrow. Okay, so today's going to be all about proportions. We're only going to look at the first 6 slides here on the lecture part. All right, so a couple of things I want to point out to you. And this is kind of gets a little bit complicated. I'm going to try many times to explain this. But ultimately, what we're going to be doing is we're going to imagine that we're going to take repeated samples over and over and over again. Okay, we're not actually going to do it because we don't have the time or the money. Okay, but we're going to imagine that we were to do that. And every time that we finish, we get a new sample proportion. Okay, every time. All right, you can do this if you have a computer. You can simulate millions of these. All right, and the amazing discovery that happened when they did this hundreds of years ago is when they plotted all of these proportions, it made this beautiful histogram that looked like a normal model. Okay, beautiful. All right, so I always love this line at the end. It's just this amazing and fortunate fact that we're going to use the normal model, which we talked about in the first semester. Okay, so we're going to use the normal model to make a sampling distribution for a sample proportion today. Okay, now a couple of notation things I want you to be aware of. If you see the letter P, this is called a population proportion. Okay, so a lowercase p is the population proportion. Pop-prop. If you see a P with a hat on it, remember that hat from the first semester? If you see a P with a hat on it, that's a sample proportion. This is a sample proportion. Okay, so make sure you know the difference between those two. P, lowercase p, is the population proportion. P hat is from a sample. All right, let's keep going. All right, now I told you guys that this was going to be a normal model, so you can see the notation here with that capital N for normal model. All right, think back many months ago, probably October, when we have a normal model, we always have a mu and a sigma. Always have a mean and a standard deviation. So our mean for these models will always be at the population proportion. Okay? And the standard deviation is going to be using this formula, the square root of PQ divided by N. And I will give that formula to you. You don't need to memorize it. Okay? So we're going to be using this a ton. Now, something that you're going to find true as we move through all this material in this entire semester is that as you look at these sampling distribution models, if your sample size increases, then your sampling distribution model, in theory, will become even more normal, okay? Even more unimodal and symmetric, okay? So there's going to be questions at some point on tests that talk about how to make something look more normal, increase the sample size. That's the way to do it. All right. Now, sorry. Okay, you're good. Okay. You're going to get really sick and tired of this, but from now until you graduate, when we do anything, especially with these models today, we have to make some assumptions. Okay? So we're going to make two assumptions today. The first one is called the independence assumption. So we are going to assume that in our sample, that our two people, or whatever it is that we're sampling, that one person's answer to something is not going to affect the next person's. Okay? We've talked about this idea of independence before in this class. Okay? And these assumptions will just be statements, guys, just a one-sentence statements. And I'll be doing an example with you where I type out the statement that I would write. The other assumption is a sample size assumption. This statement will always sound something like, our sample size of however many people is large enough. Okay, so the sample size assumption is always that our sample is large enough. Now you'll notice that these are assumptions, which we will never know if they're true. So whenever you make assumptions, you always need to check conditions. So that's a phrase you'll hear me say a lot. Make assumptions and check conditions. The conditions make us feel more confident in the assumptions that we're making. Okay? So every assumption that you make will have related conditions that you must check. Okay? Some students, after we do a bunch of these, they start to feel like most of the work they do is just checking and making assumptions, that the math part is not actually the hard part. The most challenging part is making sure you write all the stuff. Okay? So you'll be doing a lot of writing this semester. Okay, everybody good with the assumptions? Let me show you those corresponding conditions. So here are the conditions. Let me block it off so your brain can already see. Do you see these first two, the randomization and the 10% condition? Those are going to be the checks that you make for the independence assumption. And my only rule, if you're going to abbreviate assumption, is to not let it be a bad word. Okay? You can abbreviate assumption, but it cannot be a bad word. Okay? That's my only rule. Is that a bad word? Then we're okay. Okay. All right, so I'm going to do my best to show you that these are really underneath that assumption of independence that you're making. All right, so let me talk about them. Randomization condition, guys, you're just hoping that they randomly sampled. All right, and if they didn't say anything about how they sampled, then we are going to write that we think that the sample is a good representation of the entire population. All right, that's a key statement that I'm going to write today, and you'll use a lot in this class. The 10% condition, just make sure that our sample size is not too big. Okay? So the 10% condition is going to make sure that our sample size is not any bigger than 10% of the population. I'll show mathematically how you can check that one. And then the success failure condition is for the sample size assumption. Okay? There will be some work to do for that one as well. I'm pretty sure we already did that one as well in this class, the success failure condition, n times p, n times q. We've used that before, so that's coming back. All right, and I always think of this statement as the Goldilocks statement. So we need a sample that's large enough, but not too large, just right. No, Goldilocks, we don't know that story? The Three Little Bears. All right. We're almost there. So we are going to do some work today on an example. We're going to take a lot of time to do just one example so you feel confident that you can make sampling distribution models on your own going forward. All right, so this stuff here with the mean standard deviation, I already mentioned to you on a previous slide, and you will always get these as formulas. All right, so you don't need to memorize them. All right, so once you're finished with this, writing down this, we're going to do the example on the next page that talks about speeding cars. So join us on the flip side.